afternoon, everyone. Welcome to this session. I'm Mike Dixon. I'm a software developer with the Earth Engine team. Before I dive in, I also want to credit my two collaborators on this presentation. I'm the only one who was able to be in Mountain View this week, but Chris and Mathieu contributed a lot of the ideas I'm going to talk about today. So I'm going to talk, the idea of the talk is these are things you should know if you're going to try to push Earth Engine to its limits. And I'm going to do that in basically two chunks. The first half of it is going to be talking about some fairly high-level tips and tricks that honestly most people eventually stumble on if they work on Earth Engine long enough. But maybe I can save some of you the pain of rediscovering them. The second part is going to go at kind of a different approach. I'm going to dive into some of the details of how Earth Engine is executing your script, details that tend to get glossed over when you first get introduced to Earth Engine. There's some of the kind of magic that makes things really simple. And then when your script stops working because you changed something small and everything got infinitely slower, you suddenly start to realize you need to know how that magic worked and what to do to bring it back. And so that part of the talk, it'll be more diving into these are things to stay away from rather than things to do. All right. So tip number one, this one can almost always make your life better. The basic idea is that when you develop something new in Earth Engine, typically you're going to spend days or weeks or even months trying out the ideas, experimenting, refining your approach. And then at the very end, you'll do one last run to get the final data product or the final result that you want to put in your paper or make your decision based on. And that final run, you probably want to use all the available data because you want to get the best possible answer out of it. But all of those iterations up until then, if you can find a way to just work with a fraction of your data, you'll find everything goes faster, you can make progress more quickly, you can get results to guide your decision, your planning, your experiments much more quickly. Exactly how you break your data down to a smaller piece is going to depend on the structure of your data and the type of analysis you're doing. So one simple approach sometimes is just do a smaller date range. You're eventually planning to analyze 30 years of imagery, but if you start with 1 year and you do all of your experiments and preparation just using the 1 year of data, everything will go faster in the code editor and you'll get to be ready to do your final results much more quickly. Maybe that doesn't work for your data, but you could break it down by region. So instead of doing your analysis over the whole continent, you can just do it over a few selected representative spots, verify that your approach is working, validate the results, and then go back and do the whole thing at the end. Sometimes it's as simple as just saying, give me the first 100 images in the image collection instead of working with all 1,000 of them. I don't actually care which 100 I get. Sometimes working at a reduced resolution, I'll talk more about this later. If you just do all of your reduceRegion at 1/4 the resolution, you've got about 6% as many pixels to go into it, and everything's likely to be much, much faster. So nothing very sophisticated or surprising about this. It's just a approach that people often forget when they get started. They know that in the end they're going to want to do this enormous data analysis, and so they start out with that, and everything is slow and painful. All right. I told you these would be high level, right? Tip number two. Often you'll find that the computation you want to do takes a large amount of data, boils it down to some analysis, and then does subsequent things with that. And a lot of the time, if you can save the results of that first step, then when you start experimenting in the second step, everything will go a lot faster. Image collection.reduce is often a really easy place to spot this happening because you're taking a large number of images, you're consolidating them down to a single image. And then if you just save that result, every subsequent time you run your script, you can work with the saved result instead of having to recompute, reprocess all of the images in the collection. Chris had a great example of this. He built our time-lapse product, which you may be familiar with. It has a lot of high-quality visualizations of the Earth's surface. And one of the ideas that went into that was to choose a cloud threshold adaptively. So when you have a lot of Landsat scenes, you want to throw out the cloudiest ones because they throw off your composite. But how cloudy is too cloudy depends on where you are in the globe. If you're in some parts of the globe where you've got lots of high-quality imagery, you can afford to set your threshold quite high. If you're in the tropics and all your images have clouds, you want to set the threshold much lower, or else you end up with no pixels at all. So the idea was, well, we'll take these cloud scores that we have for each pixel, and in each area, we'll compute the 80th percentile of those cloud scores over all the imagery that we have, and then we can use that as a basis for setting the threshold that we're going to use to filter our images on. So that involved taking all of the images, all the image quality bands at least, and running a big reduction over them. But once we'd done that, he could export it as a saved asset, and then all of the subsequent steps just had to pull up that one saved asset, didn't have to go back to the millions of quality band images anymore, and everything could be much faster. So this is a great idea. It has some things to think about. Whenever you export an asset, whenever you export an image in Earth Engine, you have to choose a projection and a resolution. And choosing the right projection and resolution for this intermediate saved image is going to be important. In Chris's case, he wanted a global image, so he picked a plot Carré projection. He didn't need very high resolution, and so it was relatively straightforward. In your case, if you were doing a smaller region, you might want a different projection. You might want higher resolution. It'll depend on the details of your data and the details of your algorithm. The other gotcha to watch out for is this thing called a pyramiding policy. Earth Engine will compute your image at the highest resolution, but then it will also store those pixels, but then it will also store reduced versions of those pixels that will be used if you are viewing your analysis zoomed out in the code editor, for example. And the way that it reduces, the right way to reduce your data depends on what the data is and what you're using it for. There are kind of defaults, like if it's continuous data, often mean is a good answer. If it's categorical data, probably you want mode. But those aren't always the right thing. Think about your data. Think about what would be meaningful if I took 100 pixels or 1,000 pixels of your data and reduced it down to 1 pixel. What would be the representative value that you'd want to use in that scenario? I focused on images as intermediate steps because those are very common. There's other cases. If your intermediate result is a big feature collection, like the result of reduceRegions, you can save that as a feature collection asset, and then you get the same benefits. You don't have to go back to the original imagery, rerun reduceRegions each time. You just have a feature collection with the saved results in it. If you have a particularly complex geometry, sometimes the fastest way to work with it is to save it as a image, as a mask image in Earth Engine, and then you can operate much more quickly with it than you can with a very complex geometry. The third one on here, I believe isn't yet available, but I'm promised that it will be soon, which is that you'll be able to save machine learning classifiers that you compute in Earth Engine. Again, it's the same idea. You may have a large quantity of training data. If you have to recompute the classifier from that training data each time you run your script, that can potentially be very slow. If you just save the classifier and reference the saved classifier for all your subsequent steps, everything goes faster. All right. Tip number 3. This one's specifically about exporting very big images. If the product you're trying to produce is a global image at high resolution, that's probably going to take a while to export. And it's true that you can just push the button and walk away and come back a few days later, and maybe you'll get the result. But that's rarely what I would recommend. Almost always, it's worth your time to break a big image like that up into smaller pieces and do a bunch of smaller exports. There's 2 benefits to that. The first one is that you'll get the first results out in a few hours maybe instead of a few days. And if you made a mistake in your script, which occasionally people do, you'll know after a few hours instead of waiting a few days to see the whole thing going, whoops, that was a mistake, start over again. The other big benefit is that the computers that are running these exports, they're just computers. They have system issues, they have software updates. Sooner or later, that machine's going to get restarted. In fact, it's almost guaranteed to get started every week because we do software updates at about that rate. What it means when it restarts is that it basically has to restart your export from the beginning. All of the work that it had done up until that point is lost, and it starts over again. So if your export takes 3 days, and 2.5 days into that, the system gets restarted, your clock starts over again, and you're waiting another 3 days before you see any results. If you break it up into much smaller pieces, each individual piece is less likely to be affected by that because it's running for a shorter period of time. And if it does get restarted, you lose less work. So almost always, if you've got an export that's taking a day or longer, I would recommend breaking it up into smaller pieces. There's one gotcha to watch out for here. I'm not going to go into a lot of details, but if you're expecting to take the results of a bunch of export images and put them together into one large image, you'll usually want them to all be on exactly the same pixel grid. And you might think that if you specify the same projection and the same resolution, they'll be on the same grid, but that's not necessarily the case. Earth Engine will try to align the grid to match your export region, and that can sometimes mean that adjacent pieces are shifted by a fraction of a pixel, so they don't nicely join together. The way to avoid that is to use this CRS transform argument in your export, which lets you guarantee that all of the separate exports will all be on a single pixel grid, and you can reassemble them when you're done. All right, one more. This is a different kind of approach. Instead of using something like export image, you can also get your data out of Earth Engine using what we call a high volume service, which lets you make a whole lot of requests for smaller chunks of data at a time. Typically, a block of pixels that's 100 or 1,000 pixels on a side, and you might have to do thousands or hundreds of thousands of those to get all your data out. But if you're used to working with one of these frameworks, like Beam or Xarray, you'll end up writing more complex software outside of Earth Engine, but you're offloading some of the work from Earth Engine, and the whole process can go faster and get results out faster. This is especially convenient if you're going to then run the results through some other process external to Earth Engine, like a machine learning pipeline. So if you're familiar with those kinds of tools, I encourage you to look at the high volume service instead of just trying to wait for an export image each time. If you're not already familiar with writing that kind of software, it's probably not worth the hassle of learning all of that just to get your data out of Earth Engine a little bit faster, but be aware that's an option. And if you are interested in that, there's a presentation tomorrow afternoon that goes into a lot more detail. So look it up. All right, that's what I've got in the way of general strategies. The good news is that we're about halfway through. The bad news is that the second half gets a lot denser than the first half. So I'll apologize for that in advance. Where the first part was a list of things that you really should try to do, if you can, this is really things where if you do this, you'll suddenly have a bad day. Try to stay away from this problem. And because it's so dense, Chris added a bunch of puppy pictures, figuring that people whose eyes glazed over would at least have something to look at. So here we go. Number one is about pixels and projections. A lot of Earth Engine's computation is done on raster data, which is just these big arrays of pixel values. Every time Earth Engine has an array of pixel values, associated with it, it has a projection saying how those pixel values correspond to some points on the ground. When you ingest data into Earth Engine, you usually use a format like GeoTIFF, where this projection is made explicit. When you get data out of Earth Engine, it'll have a particular projection associated with it. Exactly how that's associated depends on whether you're getting tiles in the code editor viewer or you're getting an export image or whatever. But in each case, there'll be a projection for that output raster. Each of the rasters in between in those intermediate results when Earth Engine is computing stuff also has an associated projection. What makes Earth Engine great most of the time is that you don't have to specify each of the projections for each of the intermediate stages. Earth Engine figures that out automatically for you. That's kind of magical when it works. So here's to give you some intuitions about how it's working. I've got a representative Earth Engine computation over here on the right-hand side visualized as a kind of data flow diagram. So at the very top are a bunch of input images, say Landsat scenes, and I'm doing a block of computation for each one, computing NDVI, and then I'm computing a median over the NDVIs of all those images, and that's the output that I want from this particular computation. So Earth Engine, you don't write your script exactly that way. Obviously, you write it in JavaScript or Python, but Earth Engine converts it into this kind of data flow representation. And it uses that data flow in two ways. Obviously, it starts the pixels at the beginning, does this processing, and produces a result at the end. But it also actually uses this same graph in the opposite direction to help it decide what projection to use for each of these intermediate results. And the key idea there is that almost all Earth Engine algorithms need their inputs on the same grid as their outputs. So if I took this NDVI composite and I looked at it in the code editor, I'd be looking at it on a Maps Mercator image. So that's going to determine the output projection. The output is going to be Mercator, and the resolution and offset is going to depend on where my map is zoomed and scrolled to. So that combination of things determines what output projection I want for these rasters. And now, following that same rule, algorithms need their inputs in the same grid as their outputs. I can basically work my way backwards and figure out that every single one of these is going to be in that same output projection all the way until I get back to the Landsat scenes. The Landsat scenes are in their stored projection, which is usually a UTM projection at 30 meters, probably. So when I get all the way back there, I'm going to have to do some reprojection to turn the Landsat scene into the output grid that I wanted here. But once I've done that, then everything else can just filter through this data flow graph. So that's a very straightforward story, and that's how most of the time Earth Engine is deciding what projection I'm going to use for each of these intermediate rasters. Where it breaks down, not all algorithms produce rasters. Some consume rasters, some use rasters as inputs, but don't have any raster outputs. reduceRegion is sort of perhaps the most familiar one. There's other ones like reduce to vectors and sample. If you look closely, you'll see that every single one of these algorithms has arguments that let you specify the pixel grid that Earth Engine should use to prepare its input. The arguments are usually called CRS transform, and scale. And you don't have to provide all of them. In fact, you don't have to provide any of them. You can leave them all off. And then Earth Engine will use what it thinks is the default projection of the input image, which is great and convenient and all. And if the input was a stored asset, then it's easy to tell what the default projection is. It's the one that it was ingested in. And you can go look in the catalog and see what it is. If the input is anything more complicated, it's the result of some other computation, all of a sudden it gets a little harder to guess what Earth Engine is going to think the default projection is. And if Earth Engine gets it wrong, you'll be sad. Here's my effort to kind of visualize that. I don't know how well this is going to show up, but the idea here is that I'm running reduceRegions over some image. I think it's actually an elevation image. And I'm going to compute some reduceRegions is going to give me a table. But to get there, it has to first turn that image into pixels. And if I do it at a very high resolution, that's what the upper image is trying to get, I'll presumably get the most accurate set of results I could. if I do it at a somewhat reduced resolution, I'll probably get close to the same results. It depends a little on the nature of the data and the nature of the reducer. If I end up down at this resolution, chances are I'm going to get pretty inaccurate results or possibly complete garbage, because now the pixels are almost the same size as the regions that I'm trying to aggregate over. And if you are running reduceRegion and you're not specifying the projection, and the input to reduceRegions is some complex computation, you don't actually know which one of these you're getting. If you're down here, you're probably computing garbage. If you're up there, you're probably getting accurate results, but you could be doing way more computation than you need if, in fact, you don't need that many pixels to get the right result. So the only real option is to think about, when you're running these algorithms, what is an appropriate resolution for the kind of accuracy I need and for the kind of data I'm processing. Unfortunately, there's no way for Earth Engine to make that judgment for you. So anytime you're calling one of these algorithms, reduceRegion, reduceRegions, reduce to vectors, sample, things like that, if the data you're running it over isn't an ingested image where you can just point out and say, I know what the projection of that is, you should think carefully about whether you need to specify the projection and resolution. I'm focusing mostly on the resolution here because that's the most obvious problem. It's less common but possible to end up with just a completely inappropriate projection as well. The most common version of that is you end up with a UTM zone that isn't, and you're more than 5 or 10 degrees away from the proper region for that UTM zone. And then all the pixel math goes bad, and even at a low resolution, you'll be ending up with garbage. So pay attention to those projections. Think about which one's appropriate. All right, back at the beginning, I said almost all Earth Engine algorithms need their inputs on the same grid as their outputs. And the almost there hides a few exceptions. The first one most people run into is one called Reproject, which, not surprisingly, changes the projection of an image. And the way this actually works is you just say, I want the input image to be computed on this grid. It doesn't matter what the output grid is. Ignore it. Compute the input on this grid. And then after you've got the input computed on that grid, do a nearest neighbor reprojection. You might ask, why would anyone ever want to force the projection? The usual case is something like a pixel convolution algorithm. If you're doing a kernel convolution on pixels, often the kernel will only produce the right results if it's working at a particular resolution. If you've got a kernel that's trying to recognize particular kinds of features or objects, you may have designed that kernel to work at 20 meters, and so you write something like this. If you actually ran it on 2-meter imagery or 200-meter resolution imagery, you'd get no results, or you'd get garbage results or whatever. So if you're doing that kind of thing, you need to force the projection with something like this. And that basically just says, ignore the out projection, whatever the output projection is, do this computation in this projection, and then do whatever needs to happen next to use that result. The risk with doing this is it is ignoring the output projection. And if you need this, if your output projection has much lower resolution than the projection you put here, you've told Earth Engine to compute potentially thousands or millions of pixels for each output pixel. And that's just going to be slow. There's no way around it. So that's the trap people usually fall into when they start experimenting with Reproject, is they zoom out in the code editor, and all of a sudden it's incredibly slow or never finishes loading. Almost done with pixel grids, I promise. So these are a few more examples of algorithms that compute their input in a different projection than their output. Reduce resolution and interpolate are a pair of algorithms that let you control how Earth Engine shifts from, in the case of reduced resolution, from a higher resolution to a lower resolution. Interpolate is usually going the other way. If you've got low resolution data and you want to sample it at a higher resolution, it gives you control over how that works. But in both cases, they wouldn't be meaningful if the input and the output were actually in the same projection. So they don't actually have arguments saying what projection to compute the input in. they compute the input in its default projection always. And since I just told you a lot of the times you can't trust the default projection, that should set off alarms. And you should be alarmed. The way around that is this algorithm called set default projection. So anytime you're calling an algorithm like reduce resolution or interpolate, and the thing you're passing to it isn't a stored image, again, I strongly recommend that you be sure you know what projection it's going to be evaluated in. And the way to do that here is with the set default projection. All right, so it's 2 steps: set the default projection on the image, and then reduce resolution or interpolate or whatever on it. And the last group of algorithms that has this slightly funky property is the terrain slope algorithms. It turns out that computing a slope on a reprojected elevation map is a bad idea. So they always evaluate the input in its default projection again, and then reproject afterwards. And you're less likely to have a problem there because usually those are called just on the stored elevation model assets directly. But if for some reason you're computing the elevation that you want to feed into those, like you're mosaicing a bunch of DEMs together or something like that, that's the right time to use set default projection. All right, that was, I'm sure, more than anyone wanted to know about pixel grids. I'm done with them, I promise. But I'm not quite done with projections yet. So the other type of data that Earth Engine works with besides rasters is geometries and vectors. And they can have projections too. You might ask why I need a projection for a geometry. I'm putting points on the ground, and I'm drawing lines between them. What else is there to say? And of course, the problem is what it means to be a straight line is kind of problematic. What I've drawn here are 4 points in the Canadian North, and I've connected them by straight lines. In the top one, the yellow lines are straight in a Mercator projection, which means they follow lines of latitude and longitude in this case. The purple ones are straight on a spherical projection. So they're basically great circle arcs. So they're the shortest point between 2 lines on a globe. When I visualize them on a Mercator projection, obviously the yellow ones are straight because that's how I drew them, and the purple ones aren't. If I visualize them on a globe like Google Earth, all of a sudden the purple ones are straight and the yellow ones are curved. But these are the same lines, right? If you look where the yellow line goes, it's the same. It's covering the same points on the ground. They are the same line. The yellow line is the same in both. It's just straight isn't a very good concept. So that's the problem with geometry. If I'm drawing straight lines, you have to tell me which projection I'm in, and I'm going to get geometries in different projections. If geometry comes associated with raster data, it'll usually be in that raster data's projection. If it comes from some other source, it'll often be in spherical coordinates, and Earth Engine has to work with all these different representations. And Earth Engine is great. It automatically converts between all those representations for you. The catch is that converting points from one projection to another or to and from spherical coordinates is usually lossless, but converting lines isn't. The only way to convert a line from one projection or representation to another is usually to represent it by a sequence of shorter lines that approximates the curve. And Earth Engine is doing that for you automatically. It's a process we sometimes call tessellation. And you may run into this if you take a geometry from one source and you try to feed it into an algorithm that needs it in a different form. You'll also see that almost every geometry algorithm has an argument called max error, which is how good an approximation, if I have to do one of these approximations, one of these tessellations, how accurate do you want that answer to be? And the obvious answer is as accurate as possible, set max error low. But the problem is that the lower you set max error, the more line segments it's going to take to get that accurate an approximation, which means you've created a more complex geometry, which means that every subsequent thing that works with that geometry is going to be slower and require more memory. So the right answer to how much error do you want isn't the least possible. It's think about, I know this is a bad answer, but you have to think about your algorithm, you have to think about your data, you have to think about how close an approximation you really need to get the results, to get meaningful results. That's the catch with geometries and projections. And that was number 2. All right, last one. This one is about collections. Earth Engine is great because you can work with these really large collections of images, even bigger collections of features, and a lot of the time it just makes that all easy and seamless. Here's a really simple example. I'm working with this area in Western Australia, and I just want to do something with a Sentinel-2 composite. So I just show my Sentinel-2 composite on the map, or I do a reduceRegion on it or something. Last time I checked, there were about 28 million images in that collection in Earth Engine. Only about 7,000 of them actually overlap this region. So Earth Engine is counting on being able to go through that list of 28 million and pick out just the one image in 4,000 that's relevant to the thing it's trying to do. And that kind of filtering from a very large thing down to a much smaller thing is going on even if you didn't put filter bounds into your algorithm. It goes on because Earth Engine is breaking up the computation into little tiles to do the computation, and for each subtile, it wants to get just the images, just the data that's relevant to that subtile. In order to do all this, it relies on this thing called a geo-index, which is just a fast way to do this operation. Find me the rows in this table that are relevant to the area of the Earth I'm interested in. It's critical. We have a geo-index for every stored image collection. We have a geo-image for every stored feature collection. That's part of what's going on when you ingest these things, is we're building those indices so that we'll then be able to do these operations very quickly. So the problem comes up because I said we had those geo-indexes for every stored collection, but a lot of the times you want to work on a computed collection. You took each of those Sentinel-2 images and you mapped some function over the Sentinel-2 collection. You mapped a function that did cloud reduction or some kind of calibration or some other processing on it, and then you wanted to display that in your composite. And we don't have an index for your computed collection. If we had to create an index, we'd have to go look at all 28 million images in it first, compute the index. That's not going to make anything faster. Most of the time, we can avoid this problem by using this amazing trick. If you take a collection and you map a function over it, and then you filter it, that's going to give you the same result as if you filter the collection first and then map the function. So this one, I had to do 28 million runs of the function and then filter the results. Here I got to start with 4,000 and only run the function on them. So this is what I want. This is what's going to make your script run before you get old and die. And almost always, I can do this. But almost always isn't always. And the assumption that makes this valid is that the result of your function, the output image, has the same footprint as the input image. If that's true, then this is a valid optimization, and Earth Engine will go ahead and do it, and everyone will be happy. If that's not true, you're just going to have a bad time. This is my best representation of that. If you've ever had the experience of sitting there in the code editor, waiting for tiles to load, and eventually they time out, or maybe you get a couple of tiles and maybe you don't. That's kind of the experience. I'm not good at animated images, so that's the best I could do. All right, so why would your function not return an image whose footprint is the same as the input image? Almost all Earth Engine algorithms have that property. If I take an image and I add something to it, I add it to another image, the footprint's going to stay the same, or it'll be the smaller of the two footprints. Even a couple of algorithms that do make the footprint bigger, like reduce neighborhood, make it bigger in a very constrained way. They might make it 100 meters bigger if I'm, depending on what my neighborhood is, or 100 pixels. But I can work with that. I can still keep most of the original filter. Maybe I just have to adjust it a little bit. The place where I'm really going to get into trouble is if your function returns an image that has no bounds, that has an unlimited footprint. And the easy way to do that is with reducing an image collection. So here's something which people stumble on all the time. They have their function, and they actually had two versions of their function that computed image quality or something in different ways, and they just wanted to get the average of those two results. So they threw them in a collection, and they computed mean on the collection. And this sure looks like it should work. This looks like it should work just as well as either one of those functions alone would work. But it doesn't. And it doesn't work because image collection.mean always returns an unbounded image, no footprint. And if you go back to that previous slide, it's no longer valid to do the optimization that I was talking about, which means now I have to run this on every one of the 28 million images. And that's not going to work. You might ask why image collection.mean is returning an unbounded image here. The simple answer is that we had to decide what it did consistently across a lot of different use cases. And the main use case for image collection reduction is over very big image collections, like Landsat or Sentinel or something like that. And in those cases, it would take too long to go through, get the footprint of each image just to compute the footprint of the result. So we just said, OK, all image collection reduces have unbounded footprints. Simple rule, but this is where you get into trouble with it. All right. So if you think this is happening to you, here's one way you can diagnose the problem, which is, this is basically the idea. You're going to manually filter before you run your function on it. So instead of calling S2 map my function compute the median, I've now filtered S2 with this handy little thing up here, which says basically filter it to the current bounds of the map in the code editor. So in a way, this is kind of doing what the code editor was doing for you automatically. It's saying filter the collection down to what's visible in the code editor before you do all of the mapping and all of the slow processing. If that suddenly makes your problem go away, then that's pretty clear evidence that filtering was your problem. It unfortunately isn't a fix. It isn't a fix because when you export, it's not going to do the right thing. It can't. You don't want it filtered to the bounds of the code editor at the time you did the export. Even if you just scroll in the code editor, all of a sudden you'll start losing tiles because you filtered out all the images that weren't in the code editor when you started. The real thing you have to do here is to fix the original problem. And if I was going to advertise one weird trick on the internet, this would be it. You take the unbounded image that we had before, and you add those bands back to your original image. And the reason this one weird trick works is if you go read the fine print on add bands, it says the new image has the metadata and footprint from the first input image. So the result of this is always going to have the same footprint as the image it was called with. Earth Engine is able to say, OK, now I'm confident that the result of this function has the same footprint as before. Now I can do my optimization, and all of a sudden life got better again. I admit it's kind of counterintuitive. It's also sometimes annoying to have the result of your function mixed in with the original image. If that's inconvenient, here's two ways to avoid it. This is my even weirder trick. Now it's the same as before, but now I got rid of all the bands off of the image before I added on the new bands. And this seems even crazier that this would work, but it does. Selecting away all the bands of an image keeps its footprint. Adding new bands in keeps its footprint. And lo and behold, you've got something that is going to behave really nicely, even though it doesn't really make all that much sense. The other way that's in some ways much clearer about what's going on is I can take this unbounded image and I can call clip on it. And if I pass in the geometry of the original image, Earth Engine's smart enough to go, okay, this image is going to have the same footprint as that one. We're good. I actually tend to stick to one of the previous ones because this clip operation actually is potentially going to change the pixels of X. It's going to potentially require some additional computation. It might even involve tessellating a geometry. So unless you actually want the clipping, I tend to go with one of those. But this is legitimate too, and in lots of cases, it's a perfectly reasonable solution. So everyone still with me? Anyone still with me? We're done. Thank you. I'm very happy to take questions if you want to. Thank you. If you want to just run for the exits, that's OK too. Yep. So the question was, instead of calling clip, can you copy the footprint property? That is actually an interesting question. I don't know the answer to that. I think it doesn't work, but I'm not 100% sure. There's corners of Earth Engine that I always have to go try out to find. It's an interesting theory. Any other questions? Yep.
Wondering if you could go back and explain that filtered collection slide one more time, where you filtered the bounds twice. You set a variable and then you pass that variable to the filter bounds function.
This one. So the question was, what's going wrong here? Forwards or backwards? This one? Yes. OK, so the question was, what is going on here? At the top or the bottom? OK, yes. So the idea here was I wanted to find out whether my script is running slowly, and I want to find out whether the inability to filter to propagate the filter through my function is what's causing it to slow down. And the way I'm going to find out is essentially by pre-filtering my collection down to just a much smaller set of images. And this is, the first line up there is a convenient way to say, take that large collection and just reduce it down to the images that overlap the area I can currently see in the code editor. So there's a lot of assumptions there about I'm only interested in things that are currently visible in the code editor and things like that. But it's often just a very quick way to say, if I ran everything else the same, but I used a much smaller collection, would I get something out the other end? And if I do, then I know that filtering is my problem. OK. Yes? Yep. Right.
And that service is rerunning this model, or it takes a snapshot some part of the time. Because as I start panning around, my map boundary's changing. I haven't displayed the whole thing yet. What does that mean for that?
Right. So the question is, what does this actually mean? How often is that get bounds? Is it actually looking at the bounds of the map in the code editor? Is it changing every time I change the code editor? When you hit run in the code editor, it's going to, at that moment, check the bounds of the map. And that's essentially going to get saved at that point as the script. And it will be rerunning parts of the script every time it needs to get new tiles, but it won't be rerunning that part. Yeah.
Just a quick one. Can you explain one more time that shift between pixels of the same projection? Why would you get that?
Yeah. So the question was, back to export image. Why do you sometimes, if you export, do multiple image exports with the same projection and the same scale, how do you end up with them not on the same grid? If I take, for example, a UTM projection 30-meter UTM projection, I know what the overall orientation is. I know how big the pixels are. But there's still a choice of offset. I can take that same projection and offset it by a meter or 2 meters north or east or both, and it's still a 30-meter UTM projection. So when you say, I want to export this region in 30-meter UTM, Earth Engine still has to decide how much to shift the pixels. And what it does is it tries to line them up with the boundaries of the region. And you might hope that if you exported 2 regions with a shared boundary, that then they would end up with on the same pixel grid. But if your region isn't exactly an even number of pixels wide, or sometimes even if it is, if you express the region in one geometry and it has to be tessellated to get it into the other geometry, you'll end up with a sub-pixel shift, basically, on the projection that Earth Engine uses for your export, and then they won't line up anymore. Yeah?
Following up from that, is that the case when you export something to Google Drive and it gets tiled into multiple pieces? Could that shift happen?
No. So the question was, when you do a single export image to Google Drive, you can still end up with a whole bunch of images because it's limiting how many pixels it puts in a single image. When Earth Engine does that, it does keep them all on the same pixel grid. You're guaranteed that those ones should be able to reassemble. It's only when you run multiple export image operations that you have this issue of sub-pixel shifts. Yes?
Do you have any examples of unbounded feature collections?
So the question was about, are there examples of unbounded feature collections? So individual features in a collection always have a geometry associated with them. It's possible for that geometry to be global, but normally where you get into trouble is you started with a feature collection with reasonable geometries, and then you mapped a function over it that did some kind of transformation to the geometry in a way that, again, we want to do the same optimization. We want to filter the collection down to the ones that are applicable to our area. But if the function that you mapped over the feature changes its geometry in a way that Earth Engine can't predict, then it will end up having to look at every single geometry, run your function, and then determine whether the result overlaps the region of interest. That's harder to do with individual features because I can't, off the top of my head, think of any feature operations that would accidentally clobber the geometry the way that you can clobber the footprint of your images. But there might be one that I haven't thought of. It's a good question. I'll try to remember if I run into that problem. Yes? Mm-hmm. Okay. Right. So the question was, if you run reduced regions and the geometries of your regions are small relative to the pixels of the image that you're reducing over, sometimes you end up with null as a value. What's happened there is, I believe that only happens if Earth Engine doesn't think that any of the pixels, that your geometry is big enough to include any pixels. And so it has nothing to reduce. One thing to watch for is there are basically 2 kinds of reducers. There's weighted reducers and unweighted reducers. And unweighted reducers like count, when you run reduced region, it's looking for, I think the algorithm is all pixels whose center is included in your region will get reduced. Basically, with an unweighted reducer, we either have to include the pixel or not include it. Weighted reducers, we can basically, the pixels that are on the edge of the region, we can include them with a fractional weight. So we can say 30% of this pixel should be included in the sum or the mean or whatever we're computing, 10% of this pixel. Unweighted reducers, we don't have that option. We either have to put it all in or all out. And what that means is that if your geometry is small and doesn't actually include the centers of any pixels, that might mean there's no pixels to reduce. And I think that's the only case you'll get a null out of your reduced regions.
The way I kind of got around to it is basically making the scale much smaller, and then it's got return values.
Yep.
I'm wondering if the values that are returning are the values I'm looking for.
Right, so the question is, if you reduce the scale of the image that you're running reduced regions at, now you'll start to have some pixels included in your region. Are the values that are coming out meaningful? Probably. What if you looked at a visualization of what's going on, you now have pixels that are big squares and regions that are overlapping them somewhat. And Earth Engine is basically giving you what it looks like on that image. It would give you part of, 6 subpixels from here and 2 from here and 1 from here, and it would average those together or whatever your reducer does. Whether that's meaningful at that point, basically you're taking very comparatively low resolution data and trying to get a high resolution result from it. And whether that's actually useful or not, that's not a question I can answer, unfortunately. Any other questions? Yes?
Question on the next slide.
Yep.
What about updateMask?
You're a troublesome one, aren't you? I believe that updateMask leaves the, if I'm remembering correctly, updateMask leaves the footprint unchanged. I would think you would know this answer better than I do. And if that's true, then you could use it in addition to one of these, and it wouldn't affect it. But it wouldn't solve the problem for you by itself. Actually, it's possible, now that you mention it, that so updateMask takes 2 images. It's possible that if you did updateMask of the composite with the original image, that it would actually move the footprint off of the original image. That's a good question that I don't know the answer to. And
I'm wondering if it does work instead of clip, would it be more efficient?
Right, so next question is, if updateMask has the same property, which if here I said x.updateMask with image, which does somewhat similar thing, I think it's possible that it does copy the footprint for you. And would it be more efficient? Maybe. So it depends on, there's a good chance that in the process of doing this computation, it already had to compute all the pixels of image. And so accessing the mask to do this additional masking operation would be cheap. But if something else is going on here where it's doing something unexpected, it might not actually have the pixels available, in which case we'd have to compute all the pixels of image in order to get the mask, in order to do the mask operation. So maybe. My guess is that it's not going to make enough of a difference to be worth worrying about. All right, any more questions? Yes? So there were a bunch of questions there. One was, as I understand it, you were questioning whether this would actually work because it sounded like from the documentation. I'm pretty sure this works. I actually tested it out while making these slides. I can't remember exactly how the documentation of clip is worded, but I'm pretty sure that it combines the footprint of the image X with the geometry that you give it here, and that our analysis will do the right thing with this. It's possible I screwed something up in my testing, so I'll go back and check that again when we're done here. The second question was about potentially using clipToBoundsAndScale here, which is another function that does several things at once. And I wouldn't expect it to be better than clip. I would expect it to, yeah, honestly, clipToBoundsAndScale is doing enough different things that I would be reluctant to put it in my script and not know what each of the individual, whether I wanted each of the individual things that it was doing. It had a very specific intention when it was developed to be able to prepare images, the entire image that you were about to export. So if you wanted to export it, usually clipping and scaling was the very last thing you did before exporting it, and clipToBoundsAndScale was a way of making some of those steps easier, but I would be hesitant to use it in the middle of a more complex analysis like this. All right, I think we should give it a break. Thank you all very much.